Hello everyone. So let's start talking about the shapes of these orbits that we can obtain. I think it's about time to prove that they look like the way I tell you they look like. Okay. Circular orbits. I'm going to claim that this is what you need to get a circular orbit, E equals to 0, and that's a pretty easy claim to prove. The expression, the parametric expression for our orbit is the following, as we know. And of course, if E is 0, this collapses to h squared over mu, which is constant. So there's really nothing else to say, quite frankly, for circular orbits. If you have no eccentricity, or the norm of the eccentricity vector is 0, you get a constant radius, no matter what your true anomaly is. Actually, there's not even a, that's one thing that we'll explore later on, there's not even an eccentricity vector that you can define. So you choose where to start counting the theta from, because there's no E. But the R is constant, so you get a circle of M2 moving around M1. So a few things here. The velocity, the normal one, we know it's mu over h1 plus E cos theta. And this is also a constant now, because this is 0 due to E. And it's mu over h. And the radial one, of course, if it's a circle, what I'm getting, it must be 0. And in fact, it was mu over h E sine of theta, and this is 0. Makes sense. Okay. From the h equals r v perpendicular, what do I get here? That's my r. What do I want to get here? I want to get my velocity. So v, which is only v perpendicular, is h over r, right? Okay. And so this is also equivalent to square root of mu over r. Do we see that? How do you prove that? This is my r. Okay. I'm sorry, this is mu. What am I doing here? I'm getting lost. I'm sorry. Forget about this. Let's do it again. Okay, r is h squared over mu. Yeah, I was trying to prove that. What is the square root of mu over r? Is the square root of mu over this h squared mu square root. Now there was a square root missing. So it's a square root of mu squared over h squared mu over h. Here it is. Sorry, I got lost. Are we following? I'm just proving that that's my velocity. Mu over r is just a way to compute the norm of the velocity, which is only normal. You don't have a radial component. I know that this is what I should get, so I just gave it to you and I proved that that's what it is. That's one way of doing it. So I just stick the r value in here, simplify and get mu over h, which is in fact the velocity. Okay. What else? What else do we want to know about orbits? Well, we want to know about the period. How long does it take to run over this? It's a circle. So it's 2 pi r, right? Over. You can assist me here. This is very simple geometry, what we're doing. It's a bunch of formulas that we'll derive about the orbits that are useful, especially when we get to maneuvering between orbits. What do I put here? Oh, time is here. This is the period. So this is my period of the orbit. It means how long it takes to go around once. velocity. I'm going to put the velocity down there. So you can just leave it as it is if you want, or simplify the r, etc., etc. That's my period of the orbit. It only depends on the radius. That makes sense. So just so that we know where we're going this week, we're going to do all the different shapes, and at the end I will give you like a cheat sheet that summarizes all the formulas that we really need. But I want to prove them. Otherwise, it wouldn't be a senior class here. What is my energy? Energy was given by this expression minus 1 over 2 mu squared over h squared 1 minus e squared. E is 0, so I get mu squared over 2 h squared. That's it. Bless you. Now mu over h, well, it's not there anymore. But how? Well, there's a minus, right? Can I express that as a function of the radius only? Somehow. Remember, this is r, which is constant. So this is equivalent to minus mu over twice the radius. That's just another way of writing it. Do we see that? The radius is h squared over mu. If you flip it, you get mu over h squared. I add the mu. That's what I get. Yes?
What is that thing after 2 for the equation of the 2 something or?
You don't know what this is?
Yeah, what is that?
What is the length of a circle of radius r? How do you measure the length of a circle of radius r? Looks better?
That's what the actual symbol was. Okay.
Yep. Pi. You like it better?
Yeah.
Okay. I do italics here and there just to confuse people. Kind of. Okay. What else can we say about orbits? Again, I insist on the energy, and I'll do it for every single orbit, and I always will try to boil it down to a simple expression where I have something that I can quickly substitute, because the energy is what it's used, again, for maneuvering. When we go from an orbit to another, you all base it on how much energy you have to remove or add to go from an orbit to another. So we know about circular orbits. What is the radius? We know what is the velocity. We know what is the period to go around. We know the energy. I think that's pretty much all we can say. There's nothing special about circles, except, yes?
I don't understand what you mean by energy. Is that like the potential energy of the system?
The energy was well defined. Go back to the video where I did it. It's the mechanical energy is kinetic energy plus the potential energy, where this is your kinetic energy per unit mass, and this is the potential energy per unit mass. It's the total energy, or mechanical energy, which we've proven it's constant for Keplerian orbits. Okay? So you may think, okay, what's the big deal about circular orbits, except that we humans, we use them all the time around this planet, much more than anything else. So examples, well, let's start from down below, and let's try to go up. Well, let's use this side of the board. Hey, Patrick, is the audio still working? Okay, thanks. So we start from Leo. Low Earth orbits. You can find the ranges online if you want. Definition of LEO, MEO, medium Earth orbits, or geostationary Earth orbits. Books have different ranges, but usually this is below 1,000 kilometers height, 1,500 kilometers height. Now from now on, we're going to start talking about planet Earth and orbits. So that means that these r that I have all over the place, yes, they are the distances between the masses, but remember that the planet has an actual finite dimension, so has a radius, which we know it's about 6,378 kilometers. So we are up here with our spacecraft. This is r. Remember that height is r minus the radius of the Earth. So that's how they're defined. So what is in Leo? Lots of stuff. International Space Station is in Leo, about 400 plus kilometers. That's below 1,000, definitely. The shuttle used to rendezvous with the station, and it never went above Leo. Lots of Earth-observing satellites, they are pretty much a LEO. They don't fly too high if they have to take pictures. So what is one of the things that we're not modeling now, but it does exist, a LEO, that you can imagine? And then the second question is why have people always been flying a LEO, except going to the moon once, but it was a matter, or once, more than once, but it was a matter of a few days. Why haven't we been past LEO with people for months and months and months? LEO is pretty nice. Yes? Radiations. So if you remain close to the planet, there is the magnetic field of the Earth that it's kind of a shield. That's one of the issues about going to Mars, right? It's how do we shield people from cosmic radiations for months and months and months. You don't get that, well, you do get that at LEO, but the astronauts that go to the station, for example, and stay there for months, they come back and they are tested every year to study the effects on radiations, but they're still manageable. They don't get cancer right away. Probably they don't get it at all. But that's a big limitation that we have right now. We are stuck to LEO with humans because we have radiations. So that's why that's all we've done so far, because that problem is not completely solved. We want to stay months and months above that altitude. And so we have assets there. CubeSats, we're designing one CubeSat ourselves. They all go to LEO. Well, what is the other component of a low Earth orbit that I am not modeling now? Yes? Drag, right? If you are below 700 kilometers or so, you still have some atmosphere, and slowly your orbit will go down. It spirals down, and you will burn into the atmosphere. The International Space Station has to correct to regain altitude. I don't know, many weeks, pretty often. I don't know if it's a matter of weeks or months. But it does bring you down, and that has the effect of circularizing your orbit. So anything that is in LEO, even if it starts with some eccentricity, will eventually, if you don't do anything, go down to a circular orbit. And so that's enough about LEO. What do we have? Not people, though, at medium heights. Any idea? These are all circular orbits. I'm just giving you an example of circular orbits, or very close to circular orbits. GPS. GPS is, so here we said it's ISS, used to be the shuttle, we'll go there. We have CubeSats, right now universities are building them and they go up there. Observation satellites, some of them at least. If you don't have cameras, they're too fancy. Here we have definitely GPS. The height of GPS is approximately, I think the height is 20,000, 21,000 kilometers. About 31 satellites at different planes, so that unless you have buildings on top of you, you always see 3, possibly 4, and you can get your position on your cell phone these days. They're circular, close to circular. And then we go even higher, geostationary orbits. Okay? Patrick can tell you a lot about this. So why are these, well, you get two types. Circular orbits that match the period of rotation of the planet, but it can be at any inclination. Those are called geosynchronous. So it takes them 24 hours to complete one circle. But then the very interesting one and precious slots that we have are the actual geostationary orbits. So what it makes a satellite geostationary, and why are they important? Well, let's say why they are important first of all. Any ideas? I'm sorry? Spying? Yeah, telecommunication. Let's just not be classified for now, right? So if this is my planet here, right? And we assume that we have a rotation about the north-south axis with an angular velocity omega of the Earth with respect to the inertial observer. Well, then the plane which is perpendicular to that angular velocity, it's what we call the equatorial plane, right? And so, yeah. So if I'm able, say that I'm sitting down here at the equator, and if I'm able to put a satellite at the right altitude above me, and it's moving at the same angular velocity on its circular orbit as the planet, then in principle, you always see it above you, right? So several advantages. The ground track of a perfectly geostationary satellite is a point. If I start inclining the plane, of course the ground track is not a point anymore. Or if you are in any other type of orbit, you have to track the satellite. So communicating with the satellite may be not continuous, may require more ground stations. So that's the first beauty of geostationary satellites. If you are able to keep it there, you just talk to it all the time with one ground station. You can spy a pretty big chunk of the planet, as I'll show you. We'll do a couple of calculations. So for telecommunications, they're great, of course. You can anything that you can see here on the planet, you can put it in communication with another point. And so these slots, so each geostationary satellite is assigned a slot that is what, 0.1 degrees? Is that what it is, Patrick, I think? I think that's approximately right. So this angle here, it's, as far as we know, it's probably about 0.1 degree, which seems pretty small, but 0.2 degrees, it's about 300 kilometers at that height, which I haven't computed yet. So these satellites here are very high. We'll compute it. So it's very expensive to get to these orbits, fuel-wise, costs money. The more you want to go high and the more you have to spend. Once you put them in their position, so you see them where you want them to be, well, everything we're doing for now is based on this, right? But I hope we all keep in mind that this is a simple model. So if that's what we have, only that, then yes, you put a satellite exactly where it needs to be and it stays there. You always see it on top of you. But there's something else going on, right? What else is going on? The planet is not a sphere and it's not a uniform mass distribution. That's already a problem. Yes?
Things like
the moon, right? So not immediately, but at some point I'll probably touch base on three-body problems. But the moon is a pretty big object, and even though it's several hundreds of, 300,000 kilometers away or more, it does affect your motion. Especially when you're there, there's no drag, so it's a pretty important problem. And usually what it does, it tends to kick these satellites out of the equatorial plane. So that is one problem. Solar radiation pressure, and this is Patrick again. If you have satellites with reflective surfaces, the sun emits photons, and there's nothing that can stop them at these heights. They reflect on your surfaces. They give you a little bit of force. Very tiny forces. Over months and months, they accumulate and they drag you away. So bottom line, you put something above you, if you don't do anything, it's not going to stay there. It's going to drift away, do something strange, and at some point you will not see it again. So these satellites do require maneuvering. They survive for about 10 years or so. And after the 10 years, things start not working anymore, or you may want to replace them because they get obsolete. And so there's a lot of issues with them. What happens when they're not operational anymore? What do you do? It's a piece of junk, right? No one brings them down because it's probably as expensive, no, not as expensive as bringing them up, but it's a lot of fuel to bring them down and decay them into the atmosphere. So what people do is they actually push them up even more. What is called the graveyard orbit. I didn't invent this. It's not that high compared, so this is not to scale. This is about 30,000 plus kilometers. This is only another 300 kilometers. So usually these satellites are programmed in such a way that they save a little bit of fuel, not that much, so that at the end, if everything goes okay, and if the right thruster turns on, which is sometimes not the case, they give a last push and they go up and collide with other stuff, and we don't care anymore. Yes?
How do they know how to program it, fly on the Earth and burn up the Earth?
Why don't we do that? Because it would require a lot more fuel. So basically, every time you fire a thruster, when we get to maneuvering, you can approximate everything as an instantaneous change of velocity, right? You give an impulse, and you change the velocity, and you go into a new orbit. So to go from up there to down to a low Earth orbit, it's going to require a pretty big push, while raising 300, it's very small. That is the main thing. And why do we care about propellant? I mean, this is probably a lot of time, but this is useful conversation. Why do we care about propellant? It's mass that you have to bring up there. And you wouldn't want to have it, because you waste in mass that you could dedicate to sensors. It would be perfect to have a satellite that requires no fuel, no propellant, but they do. And so if we can minimize how much you have to bring up, it's like in your car. If your tank is huge, it's more weight, right? So if you can make them more efficient, you need less fuel. So this last correction here to go to the graveyard orbit, it's very small. Now, problem is that some, after 10 years of operations, they may not be able to do that. And so what happens then is that actually other satellites have to get out of the way, because these things start drifting away, and you don't want your expensive GPS satellites to be hit by something else. So it's, this GOAN line, there's a lot of images about how many satellites are in the geobelt. That's how it's called. And of course, there is a lot where there is some land below them. So there's a lot on top of the United States, Europe. Not too many on top of the Pacific Ocean, but there's some. It's pretty crowded. There's a lot of stuff up there. So let's, other questions? Yes?
I want to know, is it possible to do something to give it some eccentricity greater than 1 so it could shoot off into space?
That's even more fuel. Every correction you make to go to a different orbit, the more you want to go to a different orbit, even add eccentricity, the more thrusting it will require, which means consuming more fuel. Yep. Yeah, everything can be done, but it requires money. Yes?
So those 2 points are always at the same, it's always at that 1 point looking down at it?
That is the idea of a geostationary satellite. So let's compute, well, I'm not going to compute exactly the numbers, but I'll just show you how you do it. It's very simple. And I have the numbers here. So you want to put your satellite in a geostationary orbit, right? Which means that you want to match this angular velocity on that circle. And so what is really happening is the following, actually. If this is the sun, and this is your orbit of the Earth around the sun, now, what we call a day, or 24 hours, is the time it takes for an observer on the Earth, so this is the Earth, right, to see the sun in the same position. That's for us 24 hours. That's how we define 24 hours, right? Well, then the problem is that the Earth is rotating, say that it's rotating this way, but it's also moving on its trajectory, and so in 24 hours, it has moved a little bit on that trajectory, actually quite a bit. So this is not the right, 24-hour way of counting the 24 hours. If you're looking at the same inertial direction where the sun was, it's not going to be there. So the actual way of defining 24 hours is the time it takes for the Earth to rotate 2 pi plus this additional angle here. Let's call this alpha. Do we agree? That's how we define day. Since we rotate on our axis plus we translate on the orbit, you have to rotate a little bit more to see the sun exactly where you saw it last time. Make sense? So why am I doing this? Well, because my way of computing the angular velocity is the following. Omega E n, the norm of this, is, well, I want to divide by 24 hours. Well, then here I have to put 2 pi plus this alpha angle. I'm just going to give it to you. It's 2 pi over 365.26. Which is the duration of a year, right? That's more or less how much you need to add to see the sun again in the same position. This is in radians per second. If you do the math here, you get, what do I have? This number, 72.9217 times 10 to the minus 6 radians per second. Okay. So that's what I want to match with my circular orbit. So let's just call this, it's a scalar, right? It's just a norm. It's just call it omega e. Well, then I know how to design a circular orbit. The velocity on a circular orbit is square root of mu over r, which is also equal to omega times r. Right? Two different ways of writing the velocity on a circle. This is my geostationary satellite. Its velocity is always tangent to the circle, so that's v circular. That is always true for any circular orbit, and this is my planet here. And I'm trying to match this angular velocity. Well then, from this, I can impose mu over r geo. So I'm trying to find how high I need to be, which is equal to omega of the Earth times r geo. So I impose that my circular trajectory for the geostationary orbit has to have this angular velocity. And so if I impose this angular velocity, I'm going to call the radius that corresponds to that just r geo. Okay. Well, if you solve for that, which is not a huge deal, mu is given, omega e is that number, r geo is, let's see, I have 42,164 kilometers. That's what I have. There is one piece of information that I probably should give you once and for all, even though it's in your book. It's not really that much of a secret. Mu, if you recall, this was g, the universal constant, mass 1 plus mass 2. Well, from now on, we're looking about our planet. We're looking at our planet, so this is m Earth plus whatever is the other object. Quite frankly, unless you're talking about the moon here, you can forget about the spacecraft's mass. So let's just say that that's 0 compared to the Earth. And this is, in the appropriate units, kilometers and seconds, this is what it is. This is one of those numbers that you memorize in an astro class because you use it all the time and then you forget after a couple of weeks. Okay. Now that is the radius. That is not the height, okay? To get the height, you need to subtract the radius. So if you want to know what is the height above the ground of a geostationary orbit, you subtract the radius of the Earth, which is the number I gave you, 6,000 plus kilometers, and I get 35786 kilometers. This is several times the radius of the planet. Bless you. They're very high and, again, expensive to reach. Yes? Good.
Are all of these geocentric satellites at the same height? Like, is that a standard height?
Oh yeah, they are all in a circle. That's why it's called the geobelt. They're all in a circle that has the same radius. It's just that they are obviously at different longitudes, depending on what is it that you need to point, and if that slot is available. Because there's a lot of stuff up there. So if you want to occupy something that is already taken, you can't. In some cases, actually, if you look online and you look at those images where they show you where the satellites are, I think there are some cases where the same slot is taken by more than one. They are at slightly different heights. So they keep maneuvering them. You have to maneuver them anyhow to keep them there. So if you instead of making them exactly that radius, you change a little bit, a few hundreds of meters or maybe a few kilometers, you still have to fire a thruster every once in a while. So you can actually put them in slightly different orbits that are almost the same. And I think there are some cases where the same slot is taken by more than one, but yes. So I think it goes first, sorry.
So they're all going at the same velocity as well?
They're all going at the same velocity, so if you want to compute the same that velocity after you compute this radius right here, once you have this, your v geo is square root of mu over r geo, and that gives me, I think I have it here as well, it's about 3 0.075 kilometers per second. This is all a good exercise. You know, people don't have an idea of how things move in orbits. They don't have ballpark numbers. We should. We should definitely get a feeling. So that's how fast they go. If you go down here, the International Space Station is going about 7 kilometers per second. They go fast. So that is really a measure of how much you need to accelerate to get them there. So now, the problem is you don't have to look only, of course, at the velocity to get an idea of how expensive it is to get to a certain point. It's the change in mechanical energy that is costing you. Is this quantity here, v squared over 2 minus mu r, is how much you need to change this to go from ground to a certain altitude that it's costing you. You're fighting gravity and you want to get there with a certain velocity. Otherwise, you're not in orbit. If you get at that altitude with the wrong velocity, you either come down and destroy your satellite, or you are not in a geostationary orbit, of course. Yes?
Who manages that? Like who says what can go in what slot, and who's in charge of that?
That's a good question. Most of these things are privately operated. Well, some are Department of Defense. Of course, the Air Force has many there. So I think I believe there is a board, and it's known what is there. So you can't just go and take a slot. You need to ask permission to other operators. Otherwise, I don't know. I guess if you had the resources to put your own satellite up there in a random position and destroy another one, they will chase you down, probably. Because you're talking about several millions of dollars for one of these, and so I don't think anyone is just going to, let me try that slot. If it's free, I'll take it. Otherwise, but that's a good question. I don't know the name of the entity that actually regulates the geostationary belt, but there is one. Yeah.
I was going to ask another question. So all they have is that solid fuel, and after that, they're done. They just have to, like, they can't use.
I believe so. The solid boosters are usually, we'll get there when we talk about injecting into orbit, are usually for big maneuvering, from ground to maybe an intermediate orbit, and then at some point you use a third stage and you do another maneuver to go to the right altitude, and then you circularize. So all these things are done with big engines that are usually one time, probably solid. But once you are there, the maneuvers that are required are much smaller. So the amount of thrust that it's required is not comparable to actually changing orbits. And I believe they're probably liquid propeller. I'm not sure. It depends on the satellite.
But like you can't regenerate it with the solar panels?
Oh, regenerating the fuel, I don't know of any. Maybe there are ways out there to study how to do it. But it's still mass that you have to have on board. I don't know of a way to accumulate. If you want to fire a thruster, you're ejecting mass. So you have to have it on board already. Now, alternative ways of maneuvering in low Earth orbits, in my group we studied differential drag, or the ways of using drag to maneuver satellites with respect to each other. They still go down. They still increasingly decay in the orbit, but you can do formation flying with the drag force if you use it intelligently. Patrick and I are working on using big solar sails on geostationary satellites to see if you can adjust their orbits without using thrusters. So you have actual masses that come from the sun, in this case, the photons that reflect on your surface, and you get a push in one direction, but it's a very small one. So you're talking about maneuvers that may last months or more. Yep. But anything is great if you can save propellant, because it's not only the money and the fact that you save mass on board, is your satellite may last longer. Because these objects here, as I said, they last 10, 15 years, as far as I know. The main reason why they stop functioning or they are pushed to the graveyard orbit is because there is no more fuel. And once you've lost the fuel, there's nothing else you can do. You're just subject to all the other forces and you have no control. You're done. So, any other questions? Yes?
So they're all along the equator?
Yeah, only the equator. Because if you want a ground track, so imagine this is a ball, right? Our planet is a ball that is rotating about an axis. The only way that you can project yourself into a point on the sphere is if you're moving in the plane, which is normal to the rotation axis, and you are at the right altitude. Otherwise, any other solution will have a ground track. If you project your satellite down, that's the ground track, which it's not going to look like a point. It's impossible. Unless, but again, it boils down to costs of maneuvering. You can have an orbit that is inclined. Gosh, I keep saying that I should bring different colors, and I don't. Say that you have an orbit that is not equatorial anymore, and it's inclined at some angle, right, with respect to the equator. So there is an angle here with the equatorial plane. And in principle, you could keep your satellite in a specific location. That means you're constantly firing a thruster, which is probably a huge one. So it's not practical. No one does that. Another example of not doing certain things because they're not practical, no one launches satellites in the direction opposed to the motion of the planet. All satellites out there, even the junk, is luckily rotating in the same direction. Could you imagine the collisions otherwise? It's already pretty crowded like it is right now, but at least they're all going in the same direction. Because even if it doesn't look like, we are rotating, the velocity of our points on the planet, they're pretty fast, even if that's the omega. But the reason that the radius is not that small, it's 7 million meters. If you multiply, you get some reasonable velocity, especially at the equator. And so you want to use that. It helps you to get to the right speed on orbit, because you have to build up that speed. You have to go from whatever it's your velocity down here, depending on where you are, to say 7 kilometers per second in LEO. So no one goes that way. It looks like we're going to talk about circular orbits. I thought it was a simple thing to do, quick, but they're very interesting because we use them a lot. Let me show you one more thing about the geostationary satellites, which is, of course, of huge interest, and it's the following. How much of the planet can you see from a geostationary satellite? So this is our planet, north, south. It's just a 2D view. This would be my equatorial plane. And imagine that you have your geosatellite somewhere here. So this distance is RGeo, right? You have your satellite here. And I want to see basically how much of the planet can I see from there. And so you draw the tangent to the planet, to the satellite here, and down here, of course, the same. Ignore that this is a curved line. It shouldn't be. OK. So basically, the question could be, what is the latitude phi, maximum latitude phi that I can see from a geostationary satellite? It's your horizon, right? If you are in Florida where there is no hills, nothing, your horizon is a certain distance. If you go on the Everest, your horizon, you see more. From up there, you see a lot more. So what is the situation here? I have radius of the Earth, of course. This is a 90-degree angle. And here I have RGeo. A very simple relationship tells me that radius of the Earth is equal to radius of the geostationary orbit times the cosine of that angle phi, right? It's a simple triangle, right? And so if you solve for phi, and I'll give it to you, it's about 81 degrees. It's pretty high. If had it been 90, you would see everything, right? At least half of the planet. Well, you see almost half of the planet. This corresponds, and it's calculated in your book. I'll just give it to you. This corresponds to about 42% of the surface of the sphere, which is our planet. So you can have another one on this other side, and the two cover 84%. Except, this area here, center at the poles. You don't see this. So you may need some other type of asset to see that. But with two geostationary satellites at the exact opposites, you can see 84% of the planet, which is a lot. Yes?
How would you ever see life around the North or South Pole?
Well, you need a polar orbit. Or you can have an orbit that is inclined. Then it's a matter of how high you are. And again, you do the same operation. What is the angle that I can see if you go tangent from your position down.
Can't perfectly track those without constantly burning fuel.
Right, if you try to do like I was saying here, if you try to stay on a spot which is not natural, if you try to do something that is not natural, like firing constantly a thruster to remain on the same spot, you're not going to last long with your fuel at all. You can, again, as I said before, you can occupy a position which is close to geo, just changing the radius a little bit, and it may not cost you too much fuel to stay there. But we're talking about small modifications. If you want to do maneuvers that require a lot of delta V, that's how we'll call it, as we'll see, you may not be able to do it. Because it means that you have to have a satellite that has, it's only fuel and it's a huge mass of fuel. Okay, what else do we want to say about these? I think that's all. It's pretty cool orbits. You can do a lot of them. Do a lot with them. Telecommunications, spying people, etc. Now, one thing that you will see in your SDK, you will probably see it, at least I did when I did my own certification. Is the audio still working? I've become paranoid with that. I'm sorry. So there used to be an exercise in SDK which was about Molniya orbits. So these are developed by, were developed, I think they're still operational, by the Russians. They're not circular. They are very elliptical at high inclination. Why? Because if you think about this, if we said that we exploit the rotation of the planet to launch something into orbit, well then, how easy it is for a guy living in Russia, for example, in some locations where they can launch, which is pretty high latitude, how easy it is for this guy to put a satellite into the equatorial plane. Not easy at all, because they can launch from here, they can give an initial velocity in all sorts of directions, but mostly you want to push in the direction of the Earth. So you are constrained with a pretty high inclination, right? So these people here can really, at least for the first orbit that they can achieve, are really constrained at high inclinations. We'll talk more in details about this. And so you're either forced to, at some point where the two planes intersect, to do a correction of the inclination of the orbit, which is also a very expensive one, as we'll see. Or, again, you will see it in one exercise. Or if you want to spy a location on the planet, you can instead choose to create an orbit which is eccentric and has a very, very, very high apogee. And this is what I was going to start to do, but probably don't have time. Because as we started commenting a few lectures ago, when you're far away, your velocity is small. Why? Because h is constant. It's r crossed with v. To maintain this vector constant, if you go to pretty high radiuses, your velocity has to go down. So in very eccentric orbits, in this plane, this will look like this, right? Very eccentric. Planet is here, the Earth is here, and so in this area here, far away, you're moving very slow. It means that you're spending a lot of time here. And that's what Russians used to do. I don't know if they're still operational. To be able to cover some locations on the planet, basically they would not be able to be stationary on top of that area, but they would be able to slow down quite a bit on that area. So with a few of these, they were able to spy other locations. Yes?
So at apogee with an orbit like that, are you farther out than the geo orbit?
I don't remember the altitude of the Molniya orbits. I'll have to check it. I don't think they're higher than geo. No, I don't think so. But they're pretty high. The apogee is pretty high. So one exercise in SDK was actually, used to be at least, can I see Washington, D.C. from a Molniya orbit or something like that? I think it's still there. It's a pretty cool exercise. So, so there are alternatives for people who really cannot get access. Because really, you want to put something in geostationary orbit if you're able to access a launch location which is already at the equator or pretty close. Otherwise, it's going to be a lot of work to change your inclination, to change that plane. Now, as we still have 5 minutes, right? I was going to start looking at elliptical orbits. because it's about time, and we'll finish next time. Elliptical orbits. Why do we care about this? I think it's always good to give a justification for what we do. Okay, circular, I'm pretty sure we're convinced that they are important. We have them all over the place at all different altitudes. Well, elliptical orbits, I'll just leave you with this, are used, well, that was an example, Molniya orbits, but also we don't usually get, for example, the geobelt in one single maneuver. Sometimes we go to a lower circular orbit, we do some sanity checks, and then there is an additional maneuver that increases your radius, right? So this, I don't know, this is some radius LEO. This is, of course, not to scale. And then at some point when you're ready, you do your maneuver to go to GEO. As we will see in a few weeks, if you think about impulsive maneuvers, that's exactly what we do. We change orbit, we go to an elliptical one, we run half of that ellipse, and then here we do something else that circularizes the orbit. So you're basically flying like this. Some point here you maneuver, you change orbit, you go on an ellipse that has the apogee at GEO, for example. Then you do another maneuver. So here is maneuver 1, and here is maneuver 2. You correct your velocity so that now you become circular and you are in GEO. That's called the Hohmann transfer, as we'll see. So other than specific applications where you may want high eccentricity like this, we see elliptical orbits all the time, especially for maneuvering purposes. We start from here, of course. We know that the perigee is at theta equals 0. The apogee is at this value. So that's the closest point. This is the faraway point. And next time, what I will do, and I'll stop here, I'll start drawing the orbits as an ellipse. So I'll just state this is an ellipse, and then compute a few geometrical parameters and prove that it's actually an ellipse. Okay. And that's E. Oh, well, last piece of information. This is important. E is between 1 and 0. Without that, I can't prove it's an ellipse. Okay.